Have you ever wondered about the future of construction and materials science? Well, let's take a journey back to the 1880s, where German mathematician Hermann Schwarz visualized structures of mathematical beauty and potential strength. These structures, christened Schwarzites in his honor, have remained largely within the realm of theory until recently. Schwarzites are complex structures, with repeating patterns that lend them strength, lightness, and durability. They were the stuff of dreams and blackboards until three Brazilian physicists, Cristiano Vollner, Varley Rodrigues, and Douglas Galvao, joined forces with colleagues from Rice University in the US. Together, they developed a technique to transition these intricate structures from the abstract world of theory to the tangible world of practice. The promise of Schwarzites is immense. Imagine nanoscale electronic components, catalysts, molecular sieves, and battery components, all constructed from these strong, lightweight materials. But the potential doesn't stop there. On a larger scale, Schwarzites could be used to create robust, impact-resistant components for buildings, cars, even aircraft. The vision is so grand that one day, it might be possible to construct an entire building as if it were a single Schwarzite brick. These porous structures, which can be designed using computer algorithms, are remarkable at both the atomic and molecular scale. The team has found that they can send program data to 3D printers and build polymer models for macro-scale testing. Initial samples use the least possible amount of material while still exhibiting unparalleled strength and compressibility. What's more, these structures have shown excellent deformation characteristics. As Professor Chandra Tiwari explained, the way a material breaks is important. You don't want things to break catastrophically, you want them to break slowly. These structures are wonderful because if you apply force on one side, they deform slowly, layer by layer. Recent breakthroughs have brought Schwarzites out of the realm of theory and into the world of practical application. And this is only the beginning, as the team continues to refine and expand on Schwarz's original vision. Turns out, three Brazilian physicists have made strides in transitioning these complex structures from theory to practice. The trio, Cristiano Vollner, Varley Rodrigues, and Douglas Galvao, have been working in collaboration with colleagues from Rice University in the United States to bring the Schwarzite dream to life. Their work has resulted in the creation of a technique to build these intricate structures, a development that could potentially reshape the world around us. The result of their collaborative efforts? Strong, lightweight, and durable materials constructed from repeating complex patterns that are as beautiful as they are functional. These materials have the potential to redefine strength and versatility in a variety of practical applications. But it's not just about strength and lightness. The real beauty of these materials lies in their flexibility. Imagine a material that, while incredibly strong, can also be molded and shaped with relative ease. That's the promise of these Schwarzite-based materials. Now let's delve a bit deeper. These physicists believe that if they can refine this technique, it will enable the manufacturing of nanoscale electronic components, catalysts, molecular sieves, and battery components. That's right, the tech world could be on the brink of an exciting new era, powered by the principles of a 19th century mathematician. But the potential applications of Schwarzites don't stop at the microscopic level. On a macro scale, these materials could become robust, impact-resistant components for buildings, cars, and even aircraft. Picture this. Entire structures, as strong and intricate as they are stunning, constructed as if they were a single Schwarzite brick. In essence, the work of these three physicists, along with their colleagues at Rice University, could revolutionize everything from the smallest electronic components to the largest architectural structures. The world of Schwarzites, once confined to the realm of theory, is now taking form in the real world, and the possibilities are as infinite as the mathematical patterns that define them. These materials could revolutionize everything from electronics to construction. Imagine a world where buildings, cars, and even aircraft are constructed from Schwarzites. In the realm of the miniature, the nanoscale, Schwarzites could revolutionize the way we build electronic components. Picture a computer chip, as intricate as a city, yet no bigger than a speck of dust. These labyrinthine structures, built from repeating complex patterns, could be harnessed to manufacture catalysts, enhancing chemical reactions at a microscopic level. Transcending scales, imagine molecular sieves designed to filter out the tiniest contaminants or battery components that are not only lighter and smaller, but also significantly more efficient. But the potential of Schwarzites doesn't stop at the microscopic. Envisage the sturdiest and lightest materials you can think of. Now, take that a step further. Schwarzites could be used to create impact-resistant components for buildings, cars, and aircraft. Their unique structure, which minimizes material use while maximizing strength and compressibility, makes them a promising candidate for a wide range of macro-scale applications. Picture an entire building constructed as if it were a single Schwarzite brick. Think about the potential for architecture, pushing the boundaries of what is possible in terms of design, strength, and sustainability. Schwarzites are not just about strength and durability, though. These structures have wonderful deformation characteristics. When force is applied, they deform slowly, layer by layer, rather than breaking catastrophically. This could revolutionize safety standards in a variety of industries, from construction to automotive manufacturing. In the world of Schwarzites, the possibilities are manifold. From the atomic to the architectural, these structures have the potential to transform the way we build, the way we manufacture, and the way we live. Schwarzites could change the way we build and manufacture, making our world stronger and more efficient. As we continue to explore and refine their potential, we are only just beginning to scratch the surface of what is possible with these extraordinary structures. From theory to 3D printing, Schwarzites are being tested and refined. This is where we find ourselves in the fascinating journey of these intricate structures. The Brazilian and American teams of physicists and engineers have taken a significant leap forward by using 3D printers to build polymer models of Schwarzites for macro-scale examination. These 3D printed prototypes are the first physical manifestations of Schwarz's mathematical marvels. Crafted using intricate computer algorithms, these models have been designed to use the bare minimum of material. But don't let that fool you. They exhibit an astonishing level of strength, compressibility, and resilience, making them a promising candidate for various applications. What's truly remarkable about these structures is their deformation characteristics. Picture this. Rather than shattering under pressure, the Schwarzites gracefully yield, deforming layer by layer. It's almost as if they're telling us, "I won't break that easily, I'll give you ample warning." It's a quality that makes them incredibly desirable for applications where structural integrity is key. The team's initial tests focused on primitive and gyroid Schwarzites due to their minimal periodic surfaces. The results were uncannily consistent with the theoretical predictions for atomic-scale structures. Regardless of where the force was applied, the 3D printed prototypes distributed the load across their entire structure, a testament to their inherent strength and versatility. Now, you'd think that creating a 3D printed model of an atomic-scale structure would be a challenge, but according to Douglas Galvao, it was surprisingly doable. After a few attempts, it worked quite well, he said, highlighting the success of this theory experiment collaboration. But as with any scientific endeavor, this is just the beginning. The team plans to refine the surfaces with higher resolution 3D printers, further reducing the amount of polymer used to make the models even lighter. There's also the exciting prospect of 3D printing Schwarzites with ceramic and metallic materials and on a grander scale. These tests are just the beginning, with plans to refine the surfaces and use different materials. So as we continue to test and refine Schwarzites, we're inching ever closer to unlocking their full potential. The future of Schwarzites is as exciting as it is vast. As we step into the future, the development of Schwarzites is expected to take some thrilling turns. The team of physicists and researchers are now working towards refining the 3D printing process to create these intricate structures with even higher resolution. This will allow for an even greater level of detail, making the Schwarzite structures even more robust and versatile. But that's not all. The team is also planning to experiment with different materials for the construction of Schwarzites. While the initial prototypes were created with polymers, the future may see Schwarzites made from ceramic and metallic materials. These materials could endow the Schwarzites with additional properties, such as increased heat resistance or electrical conductivity, expanding their potential applications even further. And then, there's the question of scale. So far, the Schwarzites have been created on a relatively small scale, suitable for testing and analysis. But the team's ambitions stretch far beyond that. They aim to create larger-scale Schwarzite structures, potentially opening up a whole new world of applications. Imagine, for instance, a building constructed from Schwarzite bricks. Such a structure would not only be incredibly strong and durable, but also lightweight and efficient in its use of materials. Indeed, the potential applications of Schwarzites are as varied as they are exciting. From nanoscale electronic components and catalysts to molecular sieves and battery components, the possibilities seem endless. On a larger scale, we could see Schwarzites being used in the construction of buildings, cars, and even aircraft. The journey of Schwarzites, from a mathematical concept in the 1880s to a tangible reality in the 21st century, is a testament to the power of scientific innovation. And as we move forward, we can only expect this journey to become even more fascinating. One day, we might live in a world where Schwarzites are a common material, used in everything from electronics to buildings. The future of Schwarzites is indeed a promising one, and we can't wait to see where this journey takes us.